Hello there, and welcome to the Sleepy Space Channel. Tonight, we are exploring what it means to hold the Milky Way up against everything else there is. The Milky Way is enormous by any everyday measure. 100,000 light-years across. Hundreds of billions of stars. 1 trillion solar masses, mostly hidden in dark matter. And yet, when we lay it next to the universe gently, one rung at a time, the Milky Way begins to look smaller and smaller, until it becomes a single quiet bead in a sea of beads. We will let a soft measuring tape unroll into the dark tonight, and we will follow it slowly outward, all the way to the gentlest possible boundary there is. If you enjoy drifting off to space, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your breathing slow. Allow your eyes to grow heavy. Let the day fade away. Let's begin. Part 1. A soft place to begin. To compare the Milky Way with the universe, we first need to stand somewhere quiet. So let us begin here, in our own galaxy, with everything turned down and the night allowed to settle around us. The Milky Way is the only galaxy any of us will ever see from inside. Every other galaxy in the universe will only ever be a small, bright thing in a telescope or a soft smudge on a dark night sky. This one, the one we are inside of, is the home you cannot step outside of and look back at. So we will use it as our standing place. We will hold every other thing in the universe up to it and ask, gently, how it compares. The Milky Way is a barred spiral galaxy. It has a central bar, a slowly turning disk, and a faint envelope of older stars around it. From above, it would look a little like a slow pinwheel made of light, with two main spiral arms unwinding from each end of the bar, and several smaller spurs and branches woven between them. The disk is about 100,000 light-years across. The bulge in the middle is about 10,000 light-years thick. The whole structure, from outer arm to outer arm, is the size of a region of space that light itself would take 100,000 years to cross. We live a little more than halfway out from the center. The Sun sits about 26,000 light-years from the galactic core, on the inner edge of a small spur of stars called the Orion Arm. The Orion Arm is not one of the great main arms. It is a quieter branch, tucked between the larger Sagittarius Arm closer to the center and the Perseus Arm further out. The Sun and the Earth have been drifting along the Orion Arm for the entire history of our planet, never reaching the core, never falling away into the outer dark, just slowly, orbiting at about 220 kilometers per second through a sea of other stars doing the same. There are somewhere between 100 billion and 400 billion stars in the Milky Way. The number depends on how patient you want to be with the very small ones. If you only count the brighter, more obvious stars, the count sits closer to 100 billion. If you add in the long, faint tail of red dwarfs, small stars, that are far more common but far less visible, the number climbs toward 400 billion. Most of the stars in the Milky Way, in fact, are red dwarfs, and most of them are too dim to see with the naked eye, even from the darkest places on Earth. The disk is not thick. It is, in proportion, thinner than a record on a record player. The thin disk is about 1,000 light-years from top to bottom. The older thick disk reaches about 3,000. From a great distance, edge on, the Milky Way would look like a flattened plate of light with a soft glow at the center, not a sphere. It is a quiet, flat thing, slowly turning. Around the disk lies a much larger envelope of dark matter, a halo we cannot see, but whose gravity holds the whole galaxy together. The dark matter halo of the Milky Way reaches out for hundreds of thousands of light years in every direction. By some estimates, the gravitational influence of the Milky Way extends as far as 1,000,000 light-years from the galactic center, far beyond the visible edge of the disk. The total mass of the Milky Way, including all of that unseen halo, is roughly 1 trillion times the mass of the Sunday. The visible stars and gas make up only a small fraction of it. At the very center, hidden inside the bulge, is the quiet weight of our galaxy. A supermassive black hole weighing about 4 million suns. We call it Sagittarius A star. It is small for its kind. Some galaxies hold black holes 1,000 times heavier. But it is the anchor around which the whole Milky Way turns. Light cannot escape it. Stars near it whip around in tight, fast orbits. From where we sit, we cannot see it directly with our eyes, only its silhouette in radio waves and the gentle pull it exerts on everything nearby. The Sun has orbited the center of the Milky Way many times during the long story of the Earth. One orbit takes about 225 to 250 million years. We call this a galactic year. The Earth is about 4.5 billion years old. So the Sun has gone around the Milky Way around 20 times since the Earth formed. The first life on Earth has lived through 15 or so galactic years. All of recorded human history is a small fraction of a single galactic month. And so this is our standing place. About 100,000 light-years across. Around 100 to 400 billion stars. 1 trillion solar masses, mostly hidden. One quiet, supermassive black hole at the center. One slow, patient turning. The Milky Way is, by any everyday measure, enormous. Light itself takes 1,000 human lifetimes just to cross from one side of it to the other. We will hold every other thing in the universe up to this, and we will find that the universe gently is larger. But for now, this is the room we are in. We will not leave it suddenly. We will step outward, slowly, one room at a time. And we will keep coming back to this one, to its disk, to its slow turning, to its quiet weight at the center, because it is the one we can feel. There is a soft way to picture the Milky Way that is worth holding before we step outward. Imagine a flat plate of light, far wider than it is thick. Imagine a slow turning of that plate, with arms of stars wound gently from the center outward, as if a glowing pinwheel had been set spinning a long time ago and was still going. Imagine, in the bulge at the middle, a thicker concentration of older yellow and red stars, denser than the disk around it. Imagine, threading the disk, dark lanes of dust where new stars are quietly forming. Imagine, suspended just below and just above the disk, a faint envelope of older stars and globular clusters, small dense knots of ancient stars, left over from the early days of the galaxy. And imagine, well beyond all of that, the vast, unseen envelope of dark matter, holding everything together with a quiet weight that the eye cannot pick out. The disk is divided softly into arms. The two main arms are called Scutum Centaurus and Perseus. The smaller arms Sagittarius, Norma, and the outer arm are spurs and branches that wind between or beyond the main ones. The Orion arm, our small neighborhood, is one of those smaller spurs tucked between Sagittarius and Perseus. We do not live on a major arm. We live in a quiet side street off the great galactic highways. From here, looking inward toward the galactic center, we see one of the largest concentrations of stars in our sky, especially in the constellation Sagittarius, where the central bar of the galaxy lies behind a soft veil of dust. From here, looking outward, we see the Perseus arm and the diffuse outer disk fading into the night. The center of the galaxy is much busier than the outskirts. Within the central few thousand light-years, the density of stars climbs to perhaps 1,000 times what we have here in the disk. Stars in the galactic center orbit Sagittarius A star in tight, fast paths, some of them moving at thousands of kilometers per second, looping around the supermassive black hole on highly elliptical orbits that bring them within just a few light hours of the event horizon. From our position, on the inner edge of the Orion Arm, this central traffic is hidden behind dust. We do not see it with our eyes. We map it patiently, in radio waves, in infrared light, in X-rays, and from those patient maps, we know the Milky Way's center is one of the most extreme environments anywhere within our galaxy. The dark matter halo extends in every direction, far beyond what the eye can detect. Its boundary is gentle, not sharp. The mass density falls off softly with distance from the center, but it remains gravitationally meaningful out to roughly 1 million light-years from the galactic core. By that measure, the Milky Way and Andromeda's dark matter halos may already be touching softly, even as the two galaxies remain billions of light-years apart in their visible disks. The dark matter does not glow. It does not interact with light at all. We see it only by the way it bends the orbits of stars and the paths of light passing through galaxies. Most of the mass of the Milky Way is in that quiet, invisible envelope. Within the disk, the Milky Way is full of structures that are easy to forget, but worth holding lightly in mind. There are open clusters, loose groupings of a few hundred to a few thousand young stars, born together in the same molecular cloud and slowly drifting apart over hundreds of millions of years. There are globular clusters, dense, ancient knots of hundreds of thousands of stars, hundreds of them scattered through the halo, each one a small relic of the early universe, orbiting the galactic core on long looping paths. There are giant molecular clouds, cold, dense regions where new stars are quietly forming. There are bubbles in the interstellar medium, carved out by the winds of massive stars and the shock waves of supernovae. The local bubble, in which the Sun currently sits, is one such cavity, a region of unusually low-density gas, about 300 light-years across, carved by the explosions of nearby massive stars in the deep past. The light reaching us tonight from the far side of the Milky Way set out 100,000 years ago. That is, in its own way, a comparison worth holding. 100,000 years is roughly the entire span of behaviorally modern humanity. Some of the photons reaching your eye right now, from the far edge of our own galaxy, have been traveling since before anyone painted on the walls of any cave. They have been crossing the disk of the galaxy continuously, at the speed of light, for that entire span. They will continue to travel onward into the depths of intergalactic space after they have brushed the edge of the Earth's atmosphere. Light, in the Milky Way, is patient. The galaxy is large enough that even at the speed of light, no signal can cross it within a single human era. And so this is the room we are in, held softly. About 100,000 light-years across. About 100 to 400 billion stars. About 1 trillion solar masses with the dark matter halo counted in. One quiet supermassive black hole at the center. One slow turning. One sun, 26,000 light-years from the core, on the inner edge of one quiet arm. One Earth, 8 light minutes from one Sunday. One night, one listener, one slow breath at a time. We will hold this room. We will return to it. And from here, we will begin to step gently outward. Part 2, One Step Out, to the galaxies that come with us. The first room outward from the Milky Way is one most people forget exists. The Milky Way is not alone. It carries with it a small, quiet family of smaller galaxies, held inside its halo by the same gravity that holds the disk together. Some of these companion galaxies are bright enough to see with the naked eye from a dark place. Others are so dim that they were not even known to exist until quite recently. But every one of them is a real galaxy. Each holds its own stars, its own slow turning, its own faint history. The two best known of these companion galaxies are the Magellanic Clouds. They sit in the southern sky, visible without a telescope on a dark night below the equator, looking like two soft fragments of the Milky Way that have wandered a little off the path. The Large Magellanic Cloud is the brighter of the two. It is about 32,000 light-years, across roughly a third the width of the Milky Way, and contains about 10 billion stars. The Small Magellanic Cloud is smaller still, about 7,000 light-years across, with around 3 billion stars. The two of them sit roughly 160 to 200,000 light-years from us, orbiting the Milky Way in long, slow paths. The Magellanic Clouds are not just close. They are quietly connected to us by a long ribbon of hydrogen gas called the Magellanic Stream. This stream has been pulled out of the small cloud and partly out of the large cloud by the Milky Way's own gravity, and it now stretches in a great arc across the sky, far longer than the clouds themselves. The whole picture, if you could see it, would look like two soft, glowing patches trailing a long, thin ribbon of light behind them as they pass. Closer in, there is another companion that you cannot see. The Sagittarius dwarf spheroidal galaxy is, right now, in the slow process of being torn apart by the Milky Way's gravity. Its stars are coming unraveled in long, looping streams that wrap around our galaxy several times over. From here, this is mostly invisible. But the leftover star streams have been mapped patiently, and they trace out exactly where one small galaxy used to be before our larger one began to gently take it in. Beyond these, there is a long list of fainter neighbors. The Canis Major Dwarf, the Ursa Minor Dwarf, the Draco Dwarf, the Sculptor Dwarf, the Fornax Dwarf, Leo 1, Leo 2. Each of these is what astronomers call a dwarf spheroidal galaxy, a small, round, slow collection of older stars, with very little gas left and almost no new stars forming. They are quiet, ancient, faint. Each one of them holds anywhere from a few 100,000 stars to a few million stars. They are galaxies in every meaningful sense. They are gravitationally bound. They have their own histories. They have their own slow centers, but they are so much smaller than the Milky Way that they are easy to overlook entirely. In recent years, even fainter dwarfs have begun to be found. Some of them hold only a few thousand stars. A few thousand stars, scattered loosely across a region of space, and yet still held together by gravity by the weight of the dark matter that fills them far more thoroughly than ordinary matter ever could. Some of the smallest known galaxies are among the most dark matter-dominated objects in the universe. They are mostly invisible. They are mostly held together by something we cannot see. And they still count as galaxies, drifting alongside the Milky Way like very small ships in the wake of a very large one. If we lay these next to the Milky Way for comparison, the proportions become clear quickly. The Large Magellanic Cloud, the largest of the satellites, is about a third the Milky Way's width and a few percent of its mass. The Small Magellanic Cloud is about a tenth as wide and a fraction of a percent as massive. The smallest of the ultra-faint dwarfs is about 1/10,000th as wide as the Milky Way, and perhaps a millionth as massive. The Milky Way is the dominant galaxy in this immediate group. The others trail it. But each of them is still its own world. If you imagine standing on a planet around a star inside the large Magellanic Cloud, the Milky Way would fill a great portion of your night sky. Its full 100,000 light-year disk would lie roughly edge-on to you, a long band of stars stretching all the way across the heavens. From inside, we see the Milky Way as a soft band across our own sky on a dark night, because we are looking out from inside the disk. From the large Magellanic Cloud, the Milky Way would not be a band, it would be a great, soft wheel of light suspended above the world. It would be larger and brighter than any galaxy we ourselves can see in our own sky tonight. So the first comparison is this. The Milky Way is one galaxy, but it is the central galaxy of a small family. Around it, perhaps 50 to 60 satellite galaxies drift. Most are very small. Some are very faint. Together with the Milky Way, they make up the first room out from the home we are standing in. The room is held together by gravity. The room is held together by a much larger envelope of dark matter that none of these small galaxies could anchor by themselves. The Milky Way is, in this room, the heaviest single thing, and it is still only about half of what the room contains. Because the next step outward will introduce something heavier than the Milky Way. Something a little wider. Something whose disk has been drifting toward us very gently for a long time. And when it arrives in this story, the Milky Way will, for the first time, not be the largest object in view. The large Magellanic Cloud, taken on its own terms, would be considered a major galaxy in any neighborhood without a Milky Way or Andromeda nearby. It contains around 10 billion stars. It is rich in star-forming regions. It is home to the Tarantula Nebula, the largest star-forming complex in the local group, where some of the most massive stars known anywhere have formed and are now drifting through their short, violent lives. The Tarantula Nebula is so bright that if it were as close to us as the Orion Nebula, it would cast shadows on the Earth. Inside, it sits the dense cluster R136, a knot of stars that holds several of the heaviest stars known anywhere, stars of more than 100 solar masses, blazing out their lives in just a few million years before they collapse and explode. The small Magellanic Cloud is dimmer, smaller, and more loosely structured than its larger companion. It contains only about 3 billion stars, but it is still rich enough to host its own globular clusters, its own star-forming regions, and its own complement of variable stars, pulsing stars, whose changing brightness has, historically, been used to measure cosmic distances. The small cloud, like the large cloud, is being slowly distorted by the gravitational pull of the Milky Way. The two of them together are being pulled into long, looping orbits, and the gas inside them is being stripped out gently across the cosmic ages, forming the great Magellanic Stream that trails behind them. The Magellanic Stream is one of the largest known structures of stripped gas in the local group. It is a long ribbon of hydrogen that extends across more than 150 degrees of the sky, nearly half of the visible night. It contains hundreds of millions of solar masses of hydrogen gas, all of which has been pulled out of the Magellanic Clouds by gravitational interactions with the Milky Way. The stream is invisible to the eye, but it is bright in radio observations, glowing softly in the 21-centimeter line of neutral hydrogen. It is a faint, slow river of gas, flowing between the clouds and our own galaxy across 200,000 light-years of intergalactic space. The Sagittarius dwarf spheroidal is the next closest companion. It is a small elliptical galaxy in the process of being torn apart by the Milky Way. Its stars are scattered along a long looping stream that wraps the Milky Way's halo more than once. The Sagittarius stream is one of the most prominent stellar streams in our galaxy, and it tells the patient story of a small galaxy being slowly absorbed into a larger one. The Milky Way has done this many times in its history. The faint stars of its halo are a kind of slow record of all the smaller galaxies it has consumed across cosmic time. The ultra-faint dwarfs are a more recent discovery. Some of them hold only a few thousand stars in a region of space that, if you were inside it, would not even look like a galaxy. The stars are sparse. The space between them is large. And yet, when you measure the way those stars are moving, you find that they are bound together gravitationally far more tightly than the visible stars can account for. The implication is that ultra-faint dwarfs are mostly dark matter, perhaps 1,000 times more dark matter than ordinary matter, on average. They are the most dark matter-dominated objects we know of, and they are circling us softly in the halo of the Milky Way, almost entirely invisible. There may be many more such dwarfs that have not been found yet. The faintest of them are hard to see against the background of distant stars and galaxies. Every new generation of telescopic survey adds a few more to the catalogue. The actual count of satellite galaxies around the Milky Way may be considerably higher than the 50 to 60 currently confirmed. We are still gently mapping our own neighborhood, even at the modest scales of 100,000 to a few 100,000 light-years from the galactic center. Compared to the Milky Way, the entire ensemble of its satellites adds only a small amount of mass. The combined mass of all the dwarfs around us is perhaps 0.1% of the Milky Way's own mass. The combined stellar count is perhaps a few percent of our own. But the satellites are not without importance. They feed the Milky Way's halo with stars and gas. They contribute the long streams of stripped material that thread through our outer regions. They are part of the slow story of how a large spiral galaxy grows by gathering smaller ones into itself over cosmic time. The Milky Way today is, in part, made of the dwarf galaxies it has eaten across the last 10 billion years. And so, the first room out, the room of our satellites, is a quiet companion room. The Milky Way is the central figure. The dwarfs are the small, scattered, mostly faint companions around it. None of them rivals the Milky Way in any meaningful way. But they are part of our home neighborhood. They are part of the standing place from which we will step outward. They are the small lanterns drifting alongside the larger one. And they remind us, gently, that even at this first rung, the Milky Way is not alone. Part 3. The local group and the great companion drawing near. The next room outward is called the local group. It is the small assembly of galaxies that includes the Milky Way, all of its satellites, and the other large galaxies that are close enough to be held by mutual gravity. The local group spans about 10 million light-years from end to end. About 80 galaxies are known to belong to it. New, faint members are still being added. It is the galactic family the Milky Way belongs to. There are 3 large spiral galaxies in the local group. There is the Milky Way, where we are standing. There is the Andromeda Galaxy, our great companion. And there is the Triangulum Galaxy, the smaller third partner. Around these 3, the rest of the local group is mostly made of small dwarf galaxies, companions of the Milky Way and companions of Andromeda, plus a smaller number of isolated dwarfs drifting on their own. The Andromeda Galaxy is the senior member of this family. By disk diameter, it is about 220,000 light-years across. That is more than twice the size of the Milky Way. If we could see Andromeda the way it really is, with its full, faint outer disk, it would appear as a soft, glowing oval, many times wider than the moon in the sky. We see only a small portion of it with the naked eye, because the outer parts are too faint to register without help. But Andromeda is the most distant object the human eye can pick out on its own from a dark place. It sits about 2.5 million light-years away. That distance is worth holding for a moment. 2.5 million light-years. The light arriving from Andromeda tonight set out from there at a time when our own ancestors had only just begun walking upright. The whole story of recorded human civilization has happened in a tiny corner of the time it took that light to cross the gap between Andromeda and us. And yet, on the largest scales, 2.5 million light-years is a small distance. It is essentially the distance to our nearest large neighbor. We are, in cosmic terms, sitting on the same porch. Andromeda has its own satellite galaxies, just as the Milky Way does. Many of them are small dwarfs. 2 of them are bright, close, and visible: Messier 32 and Messier 110. Small elliptical galaxies that orbit near Andromeda's disk. They appear, in long-exposure photographs of Andromeda, as bright fuzzy companions to the larger spiral. Andromeda also has its own giant stellar stream, a long looping arc of stars that traces out the slow tearing apart of a smaller galaxy Andromeda is absorbing, much like the Sagittarius stream around the Milky Way. In total, Andromeda may contain about 1 trillion stars. That is roughly 3 times the upper estimate for the Milky Way. By that measure, Andromeda is the more populous of the 2 large spirals. But in total mass, including dark matter, the 2 are comparable. Some recent estimates even place the Milky Way slightly above Andromeda in mass, despite Andromeda's larger disk. The 2 great galaxies are, in the broadest sense, peers, companions, 2 large lanterns drifting in the same room. The 3rd large spiral, Triangulum, sits about 3 million light-years away. It is smaller than both of its companions. Its disk is about 60,000 light-years, across a little over half the width of the Milky Way. It holds about 40 billion stars, about 1/10 of the upper Milky Way count. Triangulum is not as easy to see as Andromeda. From a very dark site, it can sometimes be glimpsed as a faint smudge with the naked eye, but it requires patient looking. It is gravitationally bound to the same group, and its motion is slowly entangled with Andromeda's. Around these 3 large galaxies, the dwarf companions cluster. The Milky Way's dwarfs make a small cloud near our end of the group. Andromeda's dwarfs make a small cloud near its end. Triangulum holds a smaller number of dwarfs near it. And a few isolated dwarf galaxies float alone in the in-between, not gravitationally bound to any one of the 3 large spirals, but bound, loosely, to the group as a whole. The local group, in total, spans about 10 million light-years. The Milky Way is 100,000 light-years across. So, if we use the Milky Way as a measuring rod, the local group is about 100 Milky Way widths from end to end. Inside that 10 million light-year room, perhaps 1 trillion to 2 trillion stars are scattered across roughly 80 galaxies. The Milky Way contains a fraction of that total. By stellar count, the Milky Way holds perhaps 1/5 to 1/3 of the local group's stars. By total mass, including dark matter, the Milky Way holds about half. The other half is mostly Andromeda. There is one slow motion happening across the local group that is worth pausing on. Andromeda is drifting toward the Milky Way. It is moving in our direction at about 110 kilometers per second. That sounds fast, and on Earth it would be unimaginable. But on the scale of the local group, it is a soft drift. At that pace, Andromeda's light reaches us with a slight blue shift, a small compression of its color toward shorter wavelengths, because the gap between us is shrinking. Most distant galaxies show a redshift because they are receding due to cosmic expansion. Andromeda, the great near neighbor, is doing the opposite. In about 4 billion years, Andromeda will pass very close to the Milky Way for the first time. In about 6 to 8 billion years, the two galaxies will fully merge. The result will not be a collision in any familiar sense. Stars within galaxies are so far apart that even when two galaxies pass through each other, almost no stars actually strike one another. What will happen, slowly, is that the two disks will pull each other into long arcs and tails, and the gas in each will compress and trigger waves of new star formation, and eventually, the two will settle into a single large elliptical galaxy. Some people have given that future galaxy a soft name: Milky Way. The name is informal. The galaxy is a long way off. And recent work has even slightly softened the certainty of the merger. There is now some chance the two galaxies could pass closely without merging, depending on small details of their motion. But for now, the two galaxies are drifting toward each other, slowly and steadily, neither of them aware of the other in any meaningful sense, neither of them in any hurry, neither of them changing during any one human lifetime. Andromeda is the great companion. The Milky Way is its peer. And the local group is the room where the two of them keep each other quiet company across the long, slow patience of cosmic time. So at this rung, the comparison shifts. The Milky Way is no longer the largest object in view. The local group is. The Milky Way is one of two big galaxies in a room that is 100 times wider than itself. And the room itself is part of something larger still. Andromeda is worth holding in mind for a moment longer, because it is the largest object in our local universe and the closest other galaxy of its kind. Through a small telescope, even from a moderately dark place, Andromeda appears as a soft, elongated oval, its central bulge bright, its disk faint, and reaching outward in a long, smooth fade. With patient long-exposure photography, the disk extends much further than the eye can see, into a wide, soft halo that nearly touches our own. In real terms, Andromeda's disk reaches about 110,000 light-years from its center in every direction along the plane. Its full diameter of 220,000 light-years is the visible extent of its disk where stars can still be picked out. Beyond that disk lies Andromeda's halo, a vast envelope of older stars, globular clusters, dwarf satellites, and a tenuous gaseous bath, stretching out to more than 1 million light-years in every direction. This halo is the analog of our own. It overlaps, gently, with the Milky Way's halo at the midpoint between us. There is a real sense in which the Milky Way and Andromeda are already touching at the outermost edges of their gravitational influence, even though their visible disks are still 2.5 million light-years apart. The two galaxies are connected by a shared sea of intergalactic gas, by the gravitational pull each one exerts on the other, and by the slow drift of their cores toward each other across the long span of cosmic time. Andromeda has its own central black hole. Where the Milky Way carries 4 million solar masses at its core, Andromeda carries somewhere between 100 and 200 million. Its supermassive black hole is 40 to 50 times heavier than ours. And yet, Andromeda's black hole is also quiet, not currently feeding actively, not producing strong jets, not dominating its galaxy in any visible way. It is simply a much heavier, quiet weight at the center, anchoring the great spiral around it. From a great distance, the difference between Andromeda's core and the Milky Way's core would be barely noticeable. Both are calm. Both are old. Both have been holding their galaxies together for a long time. The Triangulum galaxy is, in some ways, more like a smaller cousin of the Milky Way than a junior version of Andromeda. Its disk is about 60,000 light-years across, with prominent spiral arms threaded by bright star-forming regions. It contains about 40 billion stars, perhaps a tenth of our upper estimate. Its central black hole, by contrast, is unusually small. There may not even be a true supermassive black hole at its core, just a denser nuclear star cluster. Triangulum is the third member of the local group's main family, and it has its own slow gravitational dance with Andromeda. They have, in fact, passed close to each other in the past, leaving distortions in both galaxies that can still be measured today. Around the three main spirals, the dwarf satellites cluster. Andromeda's two bright companions, Messier 32 and Messier 110, are easy to see in any decent image of Andromeda, small, bright, fuzzy patches near the Great Spiral, both elliptical galaxies, both gravitationally bound to it. Beyond those, Andromeda has at least 30 smaller dwarf companions, scattered through its halo, many of them found only in the last few decades through patient deep surveys. The Milky Way's satellites form their own analogous cloud around us. Triangulum has fewer, smaller satellites, in keeping with its own smaller size. A few dwarfs in the local group are not gravitationally bound to any of the three large spirals. They drift on their own through the in-between space, held loosely by the gravitational pull of the group as a whole. Examples include the Wolf-Lundmark-Merlot dwarf, IC10, NGC 6822, and Sextans A. Each is a small, isolated galaxy in the soft interior of the local group, with its own slow population of stars, its own faint star-forming regions, its own quiet existence. They are reminders that even within a tightly bound family, there are members who keep their own paths. The total stellar count of the local group is somewhere between 1 and 2 trillion stars. The Milky Way contributes a few 100 billion. Andromeda contributes roughly 1 trillion. Triangulum adds about 40 billion. The dwarfs together add perhaps a few tens of billions more. By stellar count, then, Andromeda is the more populous galaxy in the local group, and the Milky Way comes second. By total mass, the two are essentially even. The two galaxies have been drifting toward each other for a long time, and they will keep drifting until they finally interact. Andromeda's blue shift, its slight color shift, towards shorter wavelengths, because the gap between us is shrinking, has been measured for more than a century. The radial component of its motion toward us is about 110 kilometers per second. Its sideways motion, the so-called tangential velocity, is small but non-zero, and modern measurements suggest it is slightly larger than once thought. The precise details of when and how the two galaxies will pass, whether they will fully merge on the first close approach, or whether they will pass close and only merge after several more passes, depend on this small tangential motion. Recent work has softened the picture slightly. The merger is no longer considered certain. It is more probable than not within the next 10 billion years, but there is now some real chance that the two galaxies will pass closely without fully merging. Whatever happens in detail, the local group will look very different in a few billion years. Andromeda's great disk will fill more and more of our night sky as it approaches. By 2 billion years from now, it will appear noticeably larger than the full moon. By 3 to 4 billion years from now, it will fill a substantial fraction of the sky. By 5 to 7 billion years from now, the two galaxies will be in some kind of dance, either passing through each other or beginning to merge. By 10 billion years from now, if a merger does occur, the two disks will have lost their shape and a new elliptical galaxy will have formed in their place. The Earth will, by then, have been long gone. The Sun will have evolved through its red giant phase and become a slow-cooling white dwarf. Whatever observers exist in the merged Milky Way galaxy will see only the new shape of their home, not the two galaxies it came from. For now, though, the local group is in a quiet pre-merger phase. The Milky Way and Andromeda are companions across 2.5 million light-years of softly thinning intergalactic gas. The third large spiral keeps slow company off to one side. The dwarfs cluster around the bigger galaxies. The whole family drifts together through the deeper structures around it. And in the long quiet of that drifting, the Milky Way is one of two large lanterns held by the same patient gravitational pull in a room 100 times wider than itself. Part 4. The local volume and the neighbors beyond. Step a little further out from the local group and you find that we are not even the only family on the block. Other small groups of galaxies sit nearby, scattered across the next few tens of millions of light-years. Together, they make up what astronomers sometimes call the local volume, the broader neighborhood of galaxy groups within about 30 million light-years of us. The local group, with the Milky Way at its center, is one of many such groups in this volume. The Sculptor group lies about 10 to 13 million light-years away. It is anchored by a bright disk galaxy called NGC 253, the Sculptor galaxy. NGC 253 is a starburst galaxy, a galaxy with a particularly active core where many new stars are forming in a dense burst at the center. Around it, the Sculptor group includes several smaller spirals and dwarf companions. As galaxy groups go, it is a modest one. But it is the nearest other group to ours, and it lies just slightly farther out than Andromeda lies from the Milky Way. The M81 group sits about 12 million light-years away. It is anchored by two interacting spiral galaxies, Messier 81, a beautiful flocculent spiral with a quiet, bright core, and Messier 82, the Cigar galaxy, an elongated starburst galaxy that has been disturbed by close passes with its larger neighbor. Around these two large galaxies, the M81 group includes a richer collection of dwarf companions, several of them tied to M81 and several drifting on their own. The whole group is bound, gravitationally, into a more cohesive structure than the Sculptor group. The Maffei group sits about 10 million light-years away as well, but it is harder to see than the others. It hides behind the dust of the Milky Way's own plane. The two large galaxies of the group, Maffei 1 and Maffei 2, were only properly identified relatively late in astronomical history because the dust of our own disk dimmed them so heavily that earlier observers mistook them for something less interesting than they are. There is a long, thin filament of galaxies that begins with the local group, passes through the Maffei group and the IC 342 group, and continues outward, gently linking the closer galaxy groups into a soft chain. A little farther out, at about 11 to 15 million light-years, sits the Centaurus A, M83 group. This group is anchored by two of the most striking nearby galaxies, Centaurus A, a strange elliptical galaxy with a long dark band of dust cutting across its face, and Messier 83, a tightly wound spiral with bright pink star-forming regions sprinkled throughout its arms. Centaurus A is a famous object for radio astronomers because it hosts a powerful jet launched from the supermassive black hole at its core that stretches for hundreds of thousands of light-years through space. Despite its dramatic appearance, On the scale we are now using, the scale of nearby galaxy groups, it is simply one more member of the neighborhood, sitting in the room, one over from ours. If you draw the boundaries softly and count, the local volume out to about 30 million light-years from us contains perhaps a few hundred known galaxies in roughly a dozen galaxy groups. The local group is one of these. Sculptor is another. M81 is another. Maffei. Centaurus A. IC 342. The Milky Way is one large spiral inside one group inside this larger neighborhood. Many of these nearby groups also lie along a flatter structure called the local sheet. The local sheet is a thin pancake of galaxy groups, including the local group, that all drift together in roughly the same plane. It is one of the small pieces of a much larger pattern that emerges only at greater distances. You do not have to picture the local sheet too sharply. Just hold the idea softly. The galaxy groups around us are not scattered evenly in 3 dimensions. They drift, instead, on something like a slow, gentle sheet of paper, all moving together through deeper space. If we compare the Milky Way to the local volume, the comparison loosens. The Milky Way is about 100,000 light-years across. The local volume is about 30 million light-years across about 300 Milky Way widths from edge to edge. The Milky Way is one large spiral in a community of perhaps a few hundred galaxies of various sizes, organized into a dozen or so groups. It is no longer the central character. It is no longer even the central character of its own room. It is one large spiral in one group, in one neighborhood, that is itself only a small piece of a much larger pattern. And yet, even at this rung, the universe still feels familiar. The galaxy groups in the local volume look very much like our own local group. They contain large spirals and small dwarfs. They are bound together by mutual gravity. They are drifting gently together as part of a larger sheet. The pattern repeats. The shapes are recognizable. The Milky Way at this rung is not a strange object. It is a typical large spiral galaxy in a typical galaxy group in a typical local neighborhood. That, by itself, is a kind of comfort. The Milky Way is not unusual. It does not occupy a special place in the universe. It is one large lantern in a quiet stretch of cosmos, surrounded by other quiet lanterns in other quiet stretches. Each of them, in their own group, has their own equivalent of an Andromeda. Each of them has their own equivalent of dwarf companions. Each of them is held in the same kind of soft, drifting motion through a deeper structure. Beyond the local volume, that deeper structure begins to assert itself more clearly. The groups start to thicken. The voids between them start to become visible. Patterns at a much larger scale start to emerge. And we reach the next room, out the room where galaxies, instead of merely living in small groups, gather into something much grander. NGC 253, the central galaxy of the Sculptor group, is a striking example of a starburst galaxy. Its core forms new stars at a much higher rate than the Milky Way does, in some estimates 10 to 20 times faster, and the resulting flood of young, hot blue stars makes its central regions glow brightly in optical and infrared light. Around it, a handful of smaller spirals and dwarfs orbit, each with its own slower history. NGC 253 was, in fact, one of the brightest galaxies discovered relatively early in the history of southern sky astronomy, and it remains a favorite target for amateur telescopes today because of its bright disk and prominent dust lanes. The M81 group is unusual in being one of the most clearly interacting nearby groups. Messier 81 is a smooth, well-formed spiral galaxy with a relatively undisturbed disk, but its near companion Messier, 82, the cigar galaxy, has been distorted by close passes with the larger spiral. The result is one of the most dramatic starburst galaxies in our nearby cosmic neighborhood. M82 has a core, actively forming stars at a rate 10 times faster than the Milky Way's average, and powerful galactic-scale outflows of gas extend tens of thousands of light-years above and below its disk. These outflows, sometimes called superwinds, are driven by the combined energy of countless supernovae and stellar winds from the dense star-forming regions in the galaxy's heart. Watching M82 across cosmic time would be watching a galaxy in the middle of a violent reorganization, yet from a great distance, the whole interaction is silent and slow. The Maffei group is one of the most quietly remarkable nearby groups precisely because it was so easy to miss. The two largest galaxies, Maffei 1 and Maffei 2, sit in directions where the Milky Way's disk is thickest, and the dust in our own galaxy reduced their apparent brightness so dramatically that early observers did not recognize them as nearby giants. Maffei 1 is a giant elliptical galaxy, similar in some ways to a smaller cousin of the central galaxies of the Virgo Cluster. Maffei 2 is a barred spiral. Both are roughly comparable in size to the Milky Way and to Andromeda, and yet, because of dust, they were among the last nearby galaxies of their size to be identified. The reminder is a soft one. Even nearby, the universe still hides a great deal behind the small obstructions of our own galaxy's structure. Centaurus A is one of the most photographed galaxies in the southern sky. Its dark band of dust is striking it, cuts across the face of an otherwise smooth elliptical galaxy, evidence of an ancient merger between two smaller galaxies that combined to form the larger one we see now. The dust lane is the remnant of a smaller spiral galaxy whose gas was disrupted and concentrated into the central plane of the larger elliptical. Centaurus A also hosts a powerful relativistic jet, a thin beam of high-energy particles, launched from the supermassive black hole at its center that extends for more than 1 million light-years above and below the galaxy. From inside Centaurus A, that jet would be one of the dominant features of the local sky. From here, 11 million light-years away, it is a soft radio glow on long-exposure images. Messier, 83, Centaurus A's slightly more distant companion in the same group, is a tightly wound spiral galaxy with bright pink star-forming regions sprinkled throughout its arms. It is a smaller, gentler analog of the Milky Way, with similar structure and similar mass. If we wanted a soft external analog of our own galaxy, Messier 83 is one of the closest in appearance, a barred spiral with prominent arms, bright young clusters in those arms, a quiet bulge in the center, and a calm overall appearance. The local sheet, in which most of these nearby groups lie, is a wide flat structure, about 30 million light-years across in its plane, and only a few million light-years thick. It contains the local group, the M81 group, the Sculptor group, the Maffei group, the Centaurus A, M83 group, and several smaller groups. The local sheet's flatness is part of the cosmic web's larger pattern. The alignment of nearby galaxy groups along a plane is one of the early signatures, near our position, of the sheet and filament organization of the universe at much larger scales. The local sheet also has a soft motion. It is drifting, as a whole, away from a region of space below the plane called the local void. The local void is a large region of unusually low galaxy density that sits next to the local sheet, and its lack of mass relative to the surrounding universe means that the sheet is being gently pushed away from it by gravitational asymmetry. In effect, our entire neighborhood is being gently shoved by emptiness. It is a quiet, slow motion. Nothing in any human lifetime can feel it. But across cosmic time, the local sheet has been drifting upward, away from the local void, while at the same time being pulled gently inward toward the larger gravitational basins of the Virgo Cluster, the Great Attractor, and beyond. So even at this rung, the local volume, a few hundred galaxies in a dozen or so groups within 30 million light-years, the universe has a soft pattern. Groups are organized into sheets. Sheets are drifting between voids. Voids push, gravitational basins pull, and everything is in slow, gentle motion. The Milky Way is one of many large spirals at this scale, drifting in concert with the others, in a quiet sheet of galaxies, between deeper voids, toward deeper attractors. It is a quiet way to belong to the universe. Part 5, the Virgo Cluster and the thickening of galaxies. There is a part of the night sky, in the constellation Virgo, where galaxies thicken. From a deep telescopic image of that region, you would see not a single galaxy and not a small group, but hundreds upon hundreds of galaxies crowded together. Some bright, some faint, some elliptical, some spiral, some interacting, some calm. Together, they make up the nearest large cluster of galaxies to our own. It is called the Virgo Cluster. And at this rung, the comparison between the Milky Way and what surrounds us shifts again. The Virgo Cluster lies about 53 to 60 million light-years away from us. It is the nearest large cluster, a true cluster, not just a group. Where the local group holds only about 80 galaxies in a soft, loose huddle, the Virgo Cluster contains roughly 1,300 to 2,000 galaxies in a region of space about 15 million light-years across. It is denser, larger, and far more populous than any galaxy group in our immediate neighborhood. And it has the total mass to match. The Virgo Cluster weighs around 1,000 trillion times the mass of the Sun, about 1,000 times the mass of the entire Milky Way. At the heart of the Virgo Cluster sits a galaxy that, by itself, is one of the largest things any of us have ever seen. Messier 87, often abbreviated as M87, is a giant elliptical galaxy at the very center of the cluster. It is several times wider than the Milky Way's disk, and it holds several trillion stars. Most of those stars are old, slow, red, and yellow. There is very little new star formation in M87. It is an elder galaxy, the kind of galaxy that whole smaller galaxies are slowly absorbed into. And at its core, it holds a supermassive black hole of about 6.5 billion times the mass of the Sunday. That black hole is special for a small reason that has changed the way many people see the universe. It is the first black hole ever to be directly imaged in shadow. The picture that was made of it, a soft glowing ring around a small dark center suspended 53 million light-years away in space, is, in a quiet way, a picture of the boundary of one of the heaviest single objects we have ever measured. From its event horizon outward, M87's supermassive black hole would swallow the entire solar system many times over before it was full. And it is the silent center of the Virgo Cluster's brightest member, sitting calmly at the gravitational anchor of the whole cluster. Around M87, the other members of the Virgo Cluster cluster softly. M86, M84, M49, M60, M58, M59, M61. Each of these is a galaxy with hundreds of billions of stars. Each of them, on its own, would dominate any small group of galaxies it sat in. Inside Virgo, they are simply members of the population. There are dwarf elliptical galaxies orbiting them. There are infalling spirals being slowly stripped of their gas as they pass through the cluster's hot, diffuse medium. The cluster is filled with a thin, hot gas, heated to tens of millions of degrees, that fills the space between the galaxies and which glows softly in X-rays. The Virgo Cluster, like every large cluster, is more massive in this hot, diffuse gas than it is in all of its visible stars combined. The Milky Way is one of about 1,300 galaxies near Virgo, but it is not in Virgo itself. We sit about 53 million light-years from the cluster's center, on the far outer edge of Virgo's gravitational influence. The local group, in fact, is one of the smallest associations of galaxies anywhere near Virgo. We are not inside the cluster. We are not even a member of it, in the formal sense. But the cluster pulls on us. It has been pulling on us for billions of years. The Milky Way and Andromeda and the rest of the local group are slowly drifting toward Virgo at about 150 kilometers per second. Slowly enough that no human lifetime would register the change. But in cosmic terms, the local group is gently falling toward the Virgo cluster into a gravitational basin we do not have the mass to escape. If we hold the Milky Way up to the Virgo cluster, the comparison stretches. The Virgo cluster is about 15 million light-years across about 150 Milky Way widths from edge to edge. It holds about 1,300 galaxies, of which the Milky Way is, in comparison, a fairly average large spiral. It has a total mass about 1,000 times the Milky Way's, even when our dark matter halo is fully counted. By distance, the Virgo cluster is about 500 local group widths away, 53 million light-years out. At this rung, the conversation has shifted again, more dramatically. We are no longer talking about a galaxy and its small family. We are no longer talking about a small family in a quiet neighborhood. We are talking about galaxies as members of a galactic population, a population numbered in the thousands. The single galaxy is no longer the dominant character of the room. The cluster is 1,300 galaxies, moving together, held in a great gravitationally bound bath of hot, diffuse gas, anchored by a giant elliptical galaxy with a supermassive black hole at its core. This is a deeper kind of room than anything we have stepped into so far. And the Virgo cluster, large as it is only one member of something larger. Just as the Milky Way is one member of the local group, and the local group is one member of the local volume, and the local volume is one piece of a larger sheet, so the Virgo cluster, the great thickening of galaxies that sits next door to us, is only one piece of something grander still, a supercluster. The hot, diffuse gas filling the Virgo cluster is one of its most quietly remarkable features. Galaxy clusters of any reasonable size are bathed in a sea of plasma, heated to tens of millions of degrees by the gravitational potential of the cluster itself. This gas glows softly in X-rays, and it carries more mass, in many clusters, than all of the stars in all of the galaxies put together. In the Virgo cluster, the hot intracluster medium contains around 10 times the total mass of the cluster's visible stars. By total mass, this hot gas is the dominant, ordinary matter component of the cluster. The galaxies themselves are the visible peaks of a much larger plasma sea. Galaxies that fall into a cluster like Virgo are profoundly affected by this hot gas. As they move through the cluster at hundreds of kilometers per second, the dense plasma pressure can strip their gas away, a process called ram pressure stripping. Spiral galaxies that have only just fallen into Virgo are sometimes seen with long, trailing tails of gas behind them, a clear sign that their gas reservoirs are being torn out by the surrounding plasma. Over time, this stripping shuts down star formation in the infalling galaxies, slowly transforming them from active blue spirals into older, redder, gas-poor galaxies. The Virgo cluster is, in this sense, a kind of slow factory for transforming spirals into smaller ellipticals across cosmic time. The center of Virgo is dominated by M87 and a small number of other giant elliptical galaxies. These galaxies have themselves grown through the absorption of many smaller galaxies across cosmic time. The light from the central region of Virgo shows a soft sea of countless old stars that no longer belong to any particular galaxy. They belong, instead, to the cluster as a whole. This intracluster light is the residue of all the galaxies that have been disrupted as they fell into the gravitational well of Virgo over the past several billion years. The local group's fall toward Virgo has been ongoing for a long time. We are, in a soft sense, in a slow orbit around the cluster's much larger mass. The motion is unmistakable when we measure it carefully. Galaxies in our general direction show a small overall flow toward Virgo on top of the larger cosmological expansion. The phenomenon is sometimes called Virgo-centric infall, and it is one of the first measurable signs that gravity organizes the universe on scales larger than the local group. There are other clusters in the wider sky, even at this still modest distance. The Fornax cluster sits in the southern sky, about 65 million light-years away, a smaller cluster than Virgo, but still containing several hundred galaxies. The Eridanus group, slightly closer, lies in roughly the same direction. The Antlia cluster is more distant, the Hydra cluster more distant still. All of these clusters drift, in their own way, within the larger sheet of galaxies that defines our own neighborhood. The local group is, at this rung, not particularly central. It is one of many galaxy associations spread across the nearby universe, with the great mass of Virgo nearby acting as the dominant gravitational presence in our immediate cosmic vicinity. So when we compare the Milky Way to the Virgo cluster, we are comparing one large spiral to a population of 1,300 galaxies, organized around a giant elliptical core, immersed in a hot, diffuse plasma, slowly absorbing nearby groups and drifting through the deeper currents of the universe. The Milky Way is not a member of Virgo. It is a member of a smaller association on the outskirts of Virgo's gravitational influence. But the cluster has been pulling on us for billions of years, and across deep time, we will continue to fall slowly toward it. The room is wider than ours. The room has 1,300 galaxies in it. The room is just a few times further away than the local group is wide. And the Milky Way, in this room, is a small bright bead on a thin thread of infalling galaxies, drifting softly toward a much larger basin of light. Part 6. The Virgo Supercluster and the slow drift of many clusters. A supercluster is what happens when many clusters and many groups of galaxies all drift together through a gravitational basin much larger than any of them on its own. It is a kind of association at a scale so large that even an entire cluster of 1,300 galaxies becomes just one member of the larger family. And the supercluster that the Milky Way belongs to is called, simply, the Virgo Supercluster. The Virgo Supercluster takes its name from its brightest and most populous member, the Virgo Cluster. But the supercluster is far larger than that cluster alone. It extends roughly 100 to 110 million light-years across. Inside it sit about 100 galaxy groups and clusters, gathered into a long, flattened shape. The local group is one of those groups, sitting near one edge of the supercluster. The Virgo cluster sits near the center. Many other smaller clusters and groups are scattered throughout the Canes Venatici cloud, the Leo cloud, the Virgo 3 cloud, and various smaller filaments. Inside the Virgo supercluster, there are tens of thousands of galaxies. Some are large, like Andromeda and the Milky Way. Most are smaller. Many are dwarfs. Some are old, quiet ellipticals at the centers of dense clusters. Some are bright young spirals in looser, lower-density regions. Together, they form a long, flat structure, shaped a little like a great soft sheet, with the Virgo Cluster as the brightest knot of light in it. Most of the galaxies inside the Virgo Supercluster sit in a relatively narrow plane. This plane is one of the soft signatures of the cosmic web at the scale we are now exploring. Galaxy groups and clusters tend not to scatter evenly in 3 dimensions. They tend to gather along sheets and filaments, long, thin or flat structures that drift very slowly toward each other or apart, depending on the local pull of nearby mass. The Virgo Supercluster is one such sheet. The local sheet, where our local group sits, is the small piece of that larger pattern closest to us. If you imagine the supercluster from far enough away, it would look like a long, fuzzy cloud, with one bright knot at its center, smaller knots scattered through it, and long, thin fingers of galaxies stretching out from the brightest knot, like the soft arms of a stretched-out flower. The Milky Way would be a single small bead of light buried somewhere near one edge of the structure, indistinguishable to the eye from any of the other hundreds of thousands of small beads scattered through it. The Virgo Supercluster, all on its own, is 100 to 110 million light-years across. The Milky Way is 100,000 light-years across. So at this rung, the supercluster is about 1,000 Milky Way widths from edge to edge. Inside it, the Milky Way is one of perhaps tens of thousands of galaxies. The total mass of the Virgo Supercluster runs to about 1,000,000,000,000 solar masses, about 1,000 times the Milky Way's own mass, with dark matter included. For a long time, the Virgo Supercluster was thought to be the largest gravitational structure to which we belonged. The standard map of our cosmic address ended at it. Milky Way, local group, Virgo Supercluster, the end. That is how things looked for many decades. But the universe, as so often, turned out to be larger than that map. When astronomers began to map not just the positions of galaxies, but the actual motions of galaxies, the soft directions in which they were drifting through space, due to the gentle pull of all the mass around them, a different picture emerged. The Virgo Supercluster, when you mapped its motions carefully, turned out not to be a self-contained structure at all. The galaxies inside it were not, on the whole, drifting together. They were drifting along with several other neighboring superclusters, all of them flowing toward a deeper gravitational basin even further away. That deeper basin, when it was finally mapped out and named, turned out to be far larger than anyone had previously thought. It contained the Virgo Supercluster within it. It contained several other large superclusters within it as well. And it had a soft Hawaiian name, gentle and accurate at the same time. Laniakea, the immeasurable heaven. So the Virgo Supercluster, the great cosmic address that the Milky Way had been assigned to for so long, became a subdivision of something bigger. Not wrong, just smaller than the larger room around it. And the Milky Way's home address grew, quietly, by another rung. Before we step into Laniakea, though, it is worth holding the Virgo Supercluster in mind softly for a moment. Inside it, the Milky Way is one of tens of thousands of galaxies. Outside it, the Milky Way is one of trillions. Between those two numbers, the Milky Way is one bead in a slow, drifting sheet of beads, drifting itself toward the basin we are about to enter. And the sheet, on its scale, has its own motion. It is not still. It is not lonely. It is sliding, very slowly, toward something larger. The Virgo Supercluster's internal structure is not entirely smooth. It is made of a number of subunits, each of which has its own gathering of galaxies. The Canes Venatici cloud, lying close to our own local group, contains several smaller spirals and irregulars. The Leo cloud sits a little further out, in the direction of the constellation Leo, with its own collection of galaxies of various sizes. The Virgo 3 cloud, near the cluster proper, is denser and richer. These smaller substructures are all gravitationally connected through the same large web of galaxies, and they all drift together toward and around the Virgo cluster's central mass. Most of the galaxies in the Virgo Supercluster are smaller than the Milky Way. The supercluster has, by simple count, far more dwarf galaxies than large spirals or ellipticals. The bright giants Virgos M87, M86, M49, and so on, along with our own Milky Way and Andromeda, are the most prominent landmarks, but the great majority of the supercluster's population is in the long tail of smaller galaxies that orbit and drift in the spaces around them. If you could mark every galaxy in the Virgo Supercluster on a chart, the chart would look like a soft cloud of small points with a few much brighter ones scattered through it. The Milky Way would be one of the brighter points, but not the brightest. Andromeda would shine slightly brighter. Andromeda 2, our own much smaller companion, would be one of the dimmer dots. There is a soft fact worth noting at this scale. Most galaxies in the universe, at any rung you look at, are smaller than the Milky Way. The Milky Way is not a typical galaxy. In the strict statistical sense, most galaxies are dwarfs. But the Milky Way is a typical large spiral, the kind of galaxy that anchors small groups, the kind of galaxy that drifts in superclusters and clusters. So when we compare the Milky Way to the Virgo Supercluster, we are comparing a typical large spiral to a population of tens of thousands of galaxies, most of which are smaller, a handful of which are larger, and the great majority of which sit in their own quiet families across the supercluster's flattened expanse. The Virgo Supercluster, taken as a whole, is also bound less tightly than its component clusters. The clusters Virgo, Fornax, Hydra, and others are gravitationally bound objects, held together by their own internal gravity. The supercluster itself is a looser structure, organized by gravity, but not yet decoupled from the universe's overall expansion. Different parts of the supercluster drift outward from each other in proportion to their distance, much as galaxies at the largest scales drift outward from one another due to cosmic expansion. The supercluster is, in effect, a soft assembly of clusters and groups drifting together more slowly than they drift outward, but not yet bound to each other in any way that would survive the very long term. When astronomers began to study the motions of galaxies in our part of the universe more carefully, the limitations of the older Virgo supercluster boundary became clear. The Virgo supercluster is not a self-contained gravitational unit. The galaxies in our neighborhood are not, on average, falling toward Virgo. They are flowing along with the galaxies in nearby superclusters toward a deeper basin further away. The flow lines extend, smoothly, from our region into the regions around Hydra, Centaurus, and beyond, all of them pointing softly toward the same, deeper attractor. The realization that this larger basin is the actual gravitational structure to which we belong reshaped the map of our cosmic address. So the Virgo Supercluster, as a name, is still useful. It still describes a real region of the universe with real structure. But it is no longer thought of as the largest unit to which the Milky Way belongs. Instead, it is the lobe of Laniakea closest to us, the part of the larger immeasurable heaven that we are inside of. The Milky Way's home address now reads, softly, Milky Way, Local Group, Virgo Supercluster, Laniakea, and then onward into structures that have not yet been fully mapped. It is one of the gentle features of cosmology that our address can grow longer as the maps improve, but the parts of it closest to us, the Milky Way, the local group, the Virgo Supercluster, remain stable. The home is still where it is. The neighborhood is still what it is. Only the larger maps around them keep extending. The universe is patient with our maps. It does not change shape when we update them. The shapes were always there. Part 7, Laniakea, the immeasurable heaven. There is a name in Hawaiian for what surrounds us at the next rung. Laniakea. It can be translated, gently, as the immeasurable heaven or the immense heaven. It is the name astronomers gave to the deeper gravitational structure that the Milky Way and the entire Virgo Supercluster turn out to belong to. And it is, by any everyday measure, very large. Laniakea is about 520 million light-years across. To hold that against the Milky Way, which is 100,000 light-years across, is to find that Laniakea is about 5,000 Milky Way widths from edge to edge. Inside that volume drift roughly 100,000 galaxies. The total mass of Laniakea runs to about 100 million billion solar masses, roughly 100,000 times the total mass of the Milky Way, with all of its dark matter included. Laniakea is made up of 4 major components that were each, in their own right, named as superclusters before the larger structure was identified. The Virgo Supercluster, our home, sits as one lobe of Laniakea. The Hydra Centaurus Supercluster, larger than ours, is the central lobe. The Pavo-Indus Supercluster is another. The Southern Supercluster forms a fourth. Each of these 4 substructures contains many groups and clusters of galaxies. Together, they all flow toward a common gravitational basin, a deeper point of attraction near the center of Laniakea. That deeper point of attraction has a name as well. It is called the Great Attractor. The Great Attractor is a region of unusually high mass density, hidden partly behind the dust of our own Milky Way's plane, in what astronomers call the zone of avoidance, where our own galaxy blocks the view. Despite the difficulty of seeing it directly, the Great Attractor has been mapped through its gravitational pull on everything around it. Galaxies for hundreds of millions of light-years in every direction are being gently drawn toward it. The Milky Way, with the rest of the local group, with the rest of the Virgo Supercluster, with the rest of Laniakea, is among the things being drawn. The Great Attractor sits about 200 million light-years from us, roughly in the direction of the constellation Centaurus. At its core lies a cluster of galaxies called the Norma Cluster, a dense, rich cluster, partially hidden by our own galactic dust, which contains many hundreds of galaxies and a tremendous amount of mass. Around the Norma Cluster, other clusters and groups gather, all of them piled into the gravitational basin together. The total mass inside the Great Attractor's region of influence is many tens of thousands of times the mass of the Milky Way. Even beyond the Great Attractor, there is more. Roughly 650 million light-years from us, behind and beyond Laniakea, sits the Shapley Supercluster. The Shapley Supercluster is even more massive than our Great Attractor. Some recent work suggests that the Great Attractor itself is being pulled, very slowly, toward Shapley, and that what we call Laniakea may be only one lobe of an even larger basin of attraction, sometimes called the Shapley concentration, with the Shapley Supercluster as its true core. Whether the larger basin will eventually be redrawn as a single, still greater supercluster, or whether Laniakea will hold as a distinct boundary, is a question that future mapping will gently answer. For now, Laniakea is the largest gravitationally connected structure to which the Milky Way is known to belong. It is the largest soft room with our address on it. It is the home neighborhood at the largest scale where the word neighborhood still applies. Inside Laniakea, the Milky Way is one of about 100,000 galaxies. The number is large enough that it begins to feel less like a count and more like a kind of soft snowfall, with the Milky Way being one snowflake in a long, slow drift. The Milky Way is one bright bead in a soft cluster of beads, which is itself one of 4 soft clusters of beads inside Laniakea, all of them flowing toward the same gravitational basin. If you imagine Laniakea from far enough away, it would look something like a great spreading bouquet of cobwebs, with the Norma cluster at one focal point as the heaviest single bead, the Virgo cluster as another bright knot, the Hydra and Centaurus and Pavo and Indus clusters as still more bright knots, and long fingers of galaxies stretching between them, all of it slowly drifting inward toward the deepest part of the basin. The Milky Way would be one tiny bead in one tiny strand on one outer edge of that bouquet, indistinguishable from the millions of other small beads, indistinguishable from any of the other galaxies around us at this rung. And yet, even at this depth, the comparison still feels meaningful. The Milky Way is one of 100,000, but each of those 100,000 galaxies is still a real galaxy. Each has its own stars, its own slow turning, its own quiet weight at the center. Each of them, like the Milky Way, is at the heart of its own local family. Each of them, like the Milky Way, sits inside its own group, inside its own supercluster lobe, inside Laniakea, inside something larger. Laniakea, large as it is the last gravitationally meaningful structure we are part of. Beyond it, the universe stops gathering into bound objects. The patterns continue. The structures continue. The web continues. But beyond Laniakea, the universe is expanding faster than gravity can hold together. Anything larger than this room is being slowly stretched apart by cosmic expansion. The Milky Way will never gravitationally bind to anything outside Laniakea, no matter how much time passes. This makes Laniakea, in a soft way, the largest room with a name on the door that the Milky Way will ever rent. Beyond it lies the universe at a scale where gravity is no longer the dominant character. Beyond it lies the cosmic web and the great web of voids in between. The mapping of Laniakea was, in its own way, one of the soft revolutions in cosmography. For decades, astronomers had assumed that the largest gravitational structure to which we belonged was the Virgo Supercluster, a flatly drawn boundary, a name on the map, an answer to the question of where we are. The new method, which traces the actual velocity flow of galaxies through space, redrew the boundary outward. It found that the flow lines of galaxies in our region of the universe all curve gently inward toward a single, deeper basin of attraction. The boundary of Laniakea is drawn where those flow lines change direction. Outside of Laniakea, galaxies are flowing toward a different basin entirely. Inside it, they are all drifting toward ours. This kind of mapping has a soft, poetic quality. The boundary is not a wall. The boundary is the line where the slow currents of space change direction. Above the line, the river of galaxies flows one way. Below it, another. The Milky Way is in our river. The river is wide. The river is slow. And the river is flowing, gently, toward the great attractor in the heart of Laniakea. The Norma cluster, at the center of the great attractor, is a dense cluster of galaxies, similar in some ways to a smaller analog of the Virgo cluster, hidden behind the dust of our own galaxy's plane. Its position in the so-called zone of avoidance, where the Milky Way's disk blocks our view, meant that it took decades of patient observation in infrared and radio wavelengths to map properly. Even now, the full population of galaxies in the Norma cluster is only partly known, because the obscuring dust makes faint galaxies very hard to detect. But what is known is striking. The Norma cluster contains many hundreds of galaxies, and it sits at the gravitational heart of a region containing many thousands more. Around Laniakea, other large basins of attraction sit, each with its own set of superclusters flowing toward it. The Perseus-Pisces basin lies in one direction. The Coma basin lies in another. The Shapley basin lies further out still, and is, by some measurements, even more massive than ours. Some recent work suggests that all of these basins are themselves parts of a still larger superbasin that has not yet been named. The map of our cosmic address may grow further still, as the velocity flow analyses are extended to greater distances and improved precision. For now, Laniakea is the largest gravitationally connected room we know we belong to. It is the last name on our address. The room is 5,000 Milky Way widths across. It is filled with about 100,000 galaxies. Its center of attraction lies a few 100 million light-years from us, in a direction partly hidden by our own galactic dust. The flow of galaxies through space, in our neighborhood, all points softly inward toward that center. And the Milky Way is drifting with that flow very slowly, alongside every other galaxy in our portion of the supercluster. Part 8. The Cosmic Web and the Long Quiet Voids. Beyond Laniakea, the universe begins to show its largest pattern. Galaxies and superclusters do not float randomly through space. They lie along filaments, long, thin fibers of galaxies and dark matter, hundreds of millions of light-years long, that meet at nodes where galaxy clusters form. Between the filaments, broad, flat sheets of galaxies stretch out. And in between all of those filaments and sheets, the great voids open up enormous regions of near emptiness, tens to hundreds of millions of light-years across, where almost nothing is. This is the cosmic web. It is the largest pattern in the universe. It is what the universe looks like, on the very largest scales, when you stand back far enough to see everything at once. And the Milky Way is one small bead on one small filament in one small corner of it. A typical galaxy filament is somewhere between 100 million and several 100 million light-years long. It is perhaps a few tens of millions of light-years across. Inside it, galaxies are gathered into groups, into clusters, into superclusters. Laniakea is one such gathering, and the gravitational basins of those gatherings are connected by long, thin strands of galaxies and gas that thread the filament together. Some filaments are larger than that. There is a structure called the Perseus-Pisces filament, several 100 million light-years long, that stretches across one corner of the visible sky. There is a structure called the Pisces-Cetus supercluster complex, roughly 1 billion light-years long. There is the Sloan Great Wall, named for the survey that mapped it about 1.5 billion light-years long, one of the largest structures ever well confirmed by mapping. And there is the Hercules Corona Borealis Great Wall, claimed to be as much as 10 billion light-years long, though whether it is a true bound structure or a chance arrangement of galaxies is still gently debated. Some claimed structures stretch even further, at the very edges of what statistical analysis can pull cleanly from the data. To hold the Milky Way against these largest structures is a strange exercise. A single typical filament is 1,000 or more Milky Way widths long. The Sloan Great Wall is 15,000 Milky Way widths long. The Hercules Corona Borealis Great Wall if it is real, is 100,000 Milky Way widths long. At this scale, the Milky Way is no longer a measurable comparison object. It is a single thread in the weave. It is one fiber in a soft tapestry whose largest features stretch across distances so large that no listener can really hold them in mind. But we can hold them softly. We can let them pass. Between the filaments lie the voids. The voids are perhaps the strangest feature of the cosmic web. A typical void is 30 to 100 million light-years across. Inside it, the density of galaxies is roughly a tenth of the cosmic average, sometimes much less. Voids are not entirely empty. There are usually a few small galaxies drifting through them. But by everyday standards, the voids are vast soft hollows where you could travel for tens of millions of light-years in any direction and find very few galaxies, very few clusters, almost nothing to mark the passage of distance. The nearest major voids to us are several. The local void sits immediately adjacent to the local group in a region of sky toward the constellation Aquila. It is large. It is empty. And the local group, in fact, sits on the edge of it. There is some recent suggestion that the Milky Way and its nearest neighbors are not in an average region of the universe at all, that we sit in a larger underdense region called the KBC void, a soft hollow that is bigger than typical voids, and which may itself partly account for the way local galaxies are seen to drift. There is the Botez void, the most famous of the named voids, about 330 million light-years from us, and roughly 330 million light-years across. The Botez void is large enough that if our Milky Way sat at its center, the nearest other galaxies would be tens of millions of light-years away in every direction. There is the Eridanus supervoid, even larger, in the southern sky. There are many more voids, smaller and larger, scattered throughout the cosmic web. The voids, taken together, occupy roughly 60 to 80% of the volume of the universe. The cosmic web is mostly empty rooms, with thin walls between them. Most of the universe, by volume, is the voids. Galaxies and clusters and filaments occupy only a small fraction of the total space. That is a quietly remarkable fact. The Milky Way, which feels so vast to us inside, sits in a universe that is mostly empty. Most cubic megaparsecs of cosmic space contain very little. Most cubic megaparsecs of cosmic space contain almost nothing the eye could call light. The light is gathered into filaments. The filaments are thin. The voids are wide. And yet the voids are not lonely places in any meaningful sense, because the scales involved are so large that loneliness becomes a kind of category mistake. A few small galaxies do drift through every void. The galaxies that are there have plenty of internal life stars, planets, slow turning, everything we have inside the Milky Way. But in the broadest map of the cosmos, the voids are the large, soft hollows, and the filaments are the bright threads. And the Milky Way is one small bead on one of those threads, at the inner edge of a void called the local void, near the soft seam between the local sheet and the wider underdensity around us. If you imagine the cosmic web from far enough away, it would look like a great slow tangle of cobwebs, lit from inside by a soft glow of galaxies. The knots of light are clusters. The strands are filaments. The dark hollows between them are voids. The pattern repeats and repeats and repeats. Everywhere in the universe looks like this, on the largest scales. Every observer, in every galaxy, in every cluster, in every supercluster, sees the same cosmic web around them. There is no center. There is no edge, at least not in any place a traveler could reach. The Milky Way is one bead of light in one corner of that great cobweb. Held against the cobweb itself, the Milky Way is a single, small, bright spot at the meeting of two thin threads. Held against the largest filaments, the Milky Way is so small that it is no longer the right comparison object at all. And held against the voids, the great soft hollows that fill most of the universe, the Milky Way is the very small, bright thing that you would not find unless you were already pointed at it. But the cosmic web is still not the largest comparison we can make. There is one more rung above this, one final outer room. And it is the room defined not by mass or gravity, but by the speed of light and the age of the universe itself. The cosmic web is also a kind of slow record of the early universe. The shapes we see at the largest scales today, the filaments, the sheets, the voids, were already there in soft outline, in the tiny density variations of the very early cosmos. The cosmic microwave background, the faint glow from when the universe was about 380,000 years old, shows those early variations as a soft pattern of slightly warmer and slightly cooler regions. The slightly warmer regions were also slightly denser. Over billions of years, those denser regions pulled in more matter through gravity, and the slightly emptier regions slowly grew emptier as their matter drifted toward the denser regions around them. The cosmic web we see today is the grown-up shape of those original soft variations. The largest structures took the longest to form. Galaxies coalesced first, when the universe was only a few 100 million years old. Galaxy groups followed. Galaxy clusters formed across the first several billion years. Superclusters and the larger filaments are still, in some sense, forming now. The gravitational gathering of mass at the very largest scales is an ongoing process. The local group is mature. Laniakea is mature in its central parts, but still gathering at its edges. The largest filaments are still being threaded by the slow drift of galaxies into them. The voids, in turn, are slowly emptying further. Galaxies in voids are drifting toward the nearest filament. Voids are growing slightly over time as the matter in them migrates outward. The pattern is dynamic, but very slow. No human lifetime would register it. But across cosmic time, the cosmic web is becoming, very gradually, more pronounced. The filaments brighter and thicker, the voids emptier and softer. The Milky Way, perched on a thin thread, will keep its position relative to its filament for as long as the universe lasts. Part 9. The observable universe and the soft outer wall. The largest room we can compare the Milky Way to is the observable universe. The observable universe is the sphere of space from which light has had time to reach us since the universe began. Anything outside that sphere has not yet had time to send light to us. Anything inside it has, in principle, sent light that has at least begun to arrive. The universe began about 13.8 billion years ago, in the gentlest possible understanding of that phrase. Whatever the moment of beginning was, whatever the Big Bang truly was, the universe has been expanding and cooling for about that long. Light has been traveling through that universe for nearly all of that time. The oldest light we can see set out, in fact, about 380,000 years after the beginning. That light forms the cosmic microwave background, the faint and very even glow of microwaves that fills the sky in every direction. It is, in a real sense, the wall of the observable universe, the oldest light we can see, the furthest thing from us in light travel time. The light from that wall has been traveling for about 13.8 billion years to reach us. So, in light travel time, the observable universe has a radius of about 13.8 billion light-years. But because space itself has been expanding while that light was traveling, the matter that emitted that light is now much farther away than it was at the time of emission. The current distance to the cosmic microwave background, the so-called comoving distance, is about 46 billion light-years. The observable universe, in its current size, is roughly 93 billion light-years across. That is the diameter of the largest room any observer can ever map. It is the largest sphere of the universe accessible to a being standing where we stand. Inside it, somewhere between 200 billion and 2 trillion galaxies sit, each with its own population of stars, its own slow turning, its own quiet weight at the center. The exact count depends on how faint a galaxy you are willing to count. The lower estimates come from older surveys, with the Hubble Space Telescope, and the higher estimates come from more recent, deeper surveys with newer instruments. A reasonable soft number is roughly 1 trillion galaxies inside the observable universe. The Milky Way is one of them. The total number of stars inside the observable universe is even larger. Estimates run from about 200 sextillion to about 1,000 sextillion, that is, somewhere between 2 times 10 to the 22nd power and 10 to the 24th power. Numbers that large stop meaning very much as numbers. They become a kind of soft idea, a way of saying that the count is far past anything anyone has ever counted by hand. The number of stars in the observable universe exceeds the number of grains of sand on every beach and every desert on Earth combined by a wide margin. By some reckoning, there are more stars in the observable universe than there are grains of sand in the world raised to a small power. Compared to the Milky Way, the observable universe is staggering. Its diameter is about 93 billion light-years. The Milky Way is 100,000 light-years across. So the observable universe is about 930,000 Milky Way widths from edge to edge. That is almost 1 million. If you were to lay Milky Ways end-to-end across the observable universe, you would need close to 1 million of them to span the gap. By volume, the observable universe is about 1 followed by 16 zeros times the volume of the Milky Way's visible disk. By stellar count, the observable universe holds about 100 billion times as many stars as the Milky Way. By galaxy count, it holds about 1 trillion times as many galaxies as the Milky Way has galaxies, which is to say, 1 trillion times 1. By total mass, including dark matter and ordinary matter, the observable universe is roughly 10 trillion to 100 trillion times the Milky Way's mass. And yet, with all of that, the observable universe is still not the whole universe. It is only the part of it from which light has had time to reach us. The wider universe, the parts beyond the observable horizon, is almost certainly much larger. The simplest models of cosmology, the ones supported by everything we can measure, suggest that the wider universe is at least hundreds of times larger than what we can see. Some models suggest it is much larger still. Some suggest it is infinite. There is no way to measure the difference. Light has not had time to bring us news from beyond the wall. The cosmic microwave background, the soft outer wall of the observable universe, is not a wall in the way a wall is in a room. It is not solid. It is not opaque. It is simply the time edge of the universe, the boundary of when light could first travel freely. Before that time, the universe was a hot, dense plasma, and light could not travel any meaningful distance without being scattered. After that time, after about 380,000 years of cooling, the universe became transparent and light began to flow freely. The cosmic microwave background is the light from that moment, still traveling, still arriving, still cooling, as it stretches with the expansion of space. The temperature of the cosmic microwave background today is about 2.7 Kelvin, barely above absolute zero. It is the softest, faintest, most evenly spread light in the universe. It fills every cubic centimeter of space with about 400 photons. It is, in a way, the gentlest possible boundary of a room. If you imagine the observable universe from a great distance, which is, of course, an impossibility, since no observer outside the observable universe can ever exist for us, you would see a vast spherical region filled with the cosmic web, dotted with about 1 trillion galaxies, bounded by the soft outer wall of the cosmic microwave background. Inside it, somewhere, the Milky Way would be one tiny bead of light on one tiny thread of one corner of the web. From the outside, the observable universe would look like a great, soft, glowing sphere. From inside, it looks like everything there is. The wider universe, beyond the wall, may extend forever. It may be unfathomably larger. It may simply be more of the same, repeating the same cosmic web of galaxies and voids on the same scales, populated by galaxies very much like the Milky Way, and very much like Andromeda, and very much like every other galaxy we can see. The simplest assumption is that the wider universe is the same kind of place as ours. The same patterns, the same beads on the same threads, the same quiet voids between them, the same slow turning of galaxies, the same patient drift of clusters, the same gentle expansion of space carrying everything outward at the largest scales. We will never measure the wider universe directly. We will never see beyond the wall. But the wall itself is enough. Inside the observable universe, inside the largest room we can ever see, the Milky Way is one of about 1 trillion. By width, the Milky Way is about 1/1,000,000th the size. By mass, the Milky Way is about 1 in tens of trillions. By volume, it is a vanishingly small fraction of the whole. And yet, the Milky Way is also where we are. It is the standing place from which all of these comparisons are made. It is the only galaxy any of us will ever see from inside. It is the home we cannot step outside of and look back at. The largest comparison is also the softest. The Milky Way is one quiet bead in a sea of beads, in a tangle of threads, in a sphere bounded by the gentlest wall of light there is. That is what the Milky Way is compared to the universe. There is a soft fact about the observable universe that is easy to miss. Every observer in every galaxy in the universe sees their own observable universe, centered on themselves. From inside Andromeda, 2.5 million light-years away, an observer would see an observable universe of the same size as ours, but slightly shifted, they would see galaxies near our position that are at their cosmic edge, and galaxies near their own outer edge that we cannot see. From a galaxy at the edge of our own observable universe, an observer would see their own bubble extending outward in a direction we cannot reach. The universe has no center. Every observer is at the center of their own visible sphere. The structure is the same from every point. The cosmic microwave background appears equally far in every direction from anywhere you stand. The observable universe is also growing slowly, in light travel terms, simply because more time keeps passing and more light keeps reaching us. Every year, the observable universe grows a little. New light from a little further away reaches our telescopes. Galaxies that were just beyond our horizon become just within it. The growth is slow, and at very large distances, it is slowed further by the expansion of space itself. Eventually, distant galaxies recede from us so quickly that their light will never reach us. We are, at the largest scales, slowly losing galaxies to the future. Over the next 100 billion years or so, Most of the galaxies currently visible to us will fade beyond our cosmic horizon and never be seen again from this position. That slow loss is one of the gentlest features of the deep future. The local group, gravitationally bound to itself, will hold together. The merger of Andromeda and the Milky Way will produce a single elliptical galaxy at the center of a now isolated group. Distant galaxies will redshift further and further, growing dimmer and redder until they pass out of sight entirely. Eventually, far in the future, observers in our merged Milkomeda galaxy will see only their own small group of galaxies and a quiet bath of cosmic microwave background, the rest of the universe lost to the slow flood of expansion. The largest comparison we are making tonight will, in some sense, only be available for a relatively narrow window of cosmic time. We are seeing the universe at one of its most full and visible moments. For now, though, the observable universe is at its widest and most populated. 2 trillion galaxies, give or take, in a sphere 93 billion light-years across. The Milky Way is one of them. By width, by mass, by stellar count, by volume, by every measurable comparison, the Milky Way is a tiny fraction of the whole. And yet, it is the only place in that entire sphere where we have ever been able to listen to anything at all. The standing place is still the standing place, no matter how large the room around it becomes. Part 10. Returning home through the soft ladder. We began in the Milky Way. We will end in the Milky Way. Before we settle there, let us walk slowly back inward through the rooms we have crossed, holding each one softly against our home one more time. The largest comparison is the observable universe itself, about 93 billion light-years across, about 1 trillion galaxies. The Milky Way is one of them. By width, the universe is nearly 1 million Milky Way widths from edge to edge. By volume, it contains so many Milky Way volumes that the number stops being useful as a number and becomes simply a soft idea. Beyond it, the wider universe almost certainly continues much further. Possibly hundreds of times larger. Possibly infinite. We will never know. The wall of the cosmic microwave background is the gentle outer boundary of everything we can ever observe. Step inward. The cosmic web. Filaments and voids. Filaments hundreds of millions of light-years long. Voids tens to hundreds of millions of light-years across. The voids fill most of the universe by volume. The galaxies are gathered into the filaments. The Milky Way is one bead of light on one filament in one corner of the cosmic web. The Botas void, the largest single-named void near us, is about 330 million light-years across about 3,000 Milky Way widths of soft, empty room. Step inward. Laniakea, the immeasurable heaven, about 520 million light-years across, about 5,000 Milky Way widths, about 100,000 galaxies. The Great Attractor, at its gravitational center, hidden behind the dust of our own galaxy. 4. Major superclusters: Virgo, Hydra Centaurus, Pavo Indus, and the Southern Supercluster, all flowing softly inward together. The Milky Way is one bead in this bouquet. Laniakea is the last gravitationally bound room we belong to. Beyond it, the universe expands faster than gravity can hold it. Step inward. The Virgo Supercluster, about 100 to 110 million light-years across, about 1,000 Milky Way widths, about 100 groups and clusters of galaxies, tens of thousands of individual galaxies. The Virgo Cluster as its bright knot, the local group near one edge. Step inward. The Virgo Cluster, about 15 million light-years across, about 150 Milky Way widths, about 1,300 galaxies. The giant elliptical M87 as its central anchor, a supermassive black hole of 6.5 billion solar masses at the heart of it. The local group falling slowly toward it at 150 kilometers per second. Step inward. The local volume, about 30 million light-years across, about 300 Milky Way widths. A few hundred known galaxies in about a dozen groups: Sculptor, M81, Centaurus A and M83, Maffei, IC, 342, and others. The local sheet as the flatter pattern within which they all drift. Step inward. The local group, about 10 million light-years across, about 100 Milky Way widths, about 80 galaxies, 3 large spirals, the Milky Way, Andromeda, and Triangulum, dwarfs in soft clouds around each of the large spirals, Andromeda drifting toward us at 110 kilometers per second, slowly closing the gap of 2.5 million light-years between us. Step inward. The Milky Way and its satellites. The Magellanic Clouds at 160 to 200,000 light-years out, the Large Magellanic Cloud, about a third the Milky Way's width, the Small Magellanic Cloud, smaller still. The Sagittarius Dwarf coming unraveled around us. Dozens of smaller dwarfs scattered through our halo. The Magellanic Stream of stripped hydrogen trailing behind. Step inward. The Milky Way itself, about 100,000 light-years across, 100 to 400 billion stars, 1 trillion solar masses with dark matter included. Sagittarius A star at the quiet center, 4 million solar masses inside a region smaller than our solar system. The Sun, on the inner edge of the Orion Arm, 26,000 light-years from the galactic core, having orbited the galaxy about 20 times during the long story of the Earth. Step inward further, just a little. The solar system. 8 planets, several dwarf planets, the asteroid belt, the Kuiper belt, the heliopause where the solar wind meets interstellar space, the Oort cloud reaching out to about a light-year or so in every direction. The Sun, one ordinary yellow star among hundreds of billions. Step inward further. The Earth. One pale blue dot, third planet from the Sun, 8 light minutes from its nearest star. Home to everything you have ever touched. The only place in the universe where, as far as we know with any certainty, anyone is currently listening. The whole walk fits, somehow, inside the same gentle sentence. The Milky Way is one galaxy among about 1 trillion. It is the standing place for everything we have ever measured. It is 100,000 light-years across, and the universe is nearly 1 million times wider, and the wider universe beyond what we can see may be larger by a factor we cannot say. And yet, when light from the wall of the universe arrives here, on a quiet night, it lands in the Milky Way, on the Earth, in your eye, with you in it. Every comparison passes through you on its way back home. There is a soft phrase to hold on to as you drift. You live in a galaxy that holds hundreds of billions of stars. That galaxy is one of trillions. The trillions are gathered into a sphere that is itself only a small portion of a wider universe whose outer edges we cannot reach. And yet, your shoulders are still where they always were. Your breath is still moving in and out of you, soft and slow. The galaxies continue their patient turning, and Andromeda continues its long drift toward us, and Laniakea continues its slow flow toward the Great Attractor. and the cosmic web continues its quiet weave through the voids, and none of it requires anything of you at all. And so we leave the Milky Way, where we found it turning slowly inside a much greater pattern that has been there all along. The largest things you have heard of tonight will not change shape in any human lifetime, and they will keep their shape long after this night has been forgotten. Let your shoulders soften. Let your breathing slow. Let the long quiet hold you for a while. Sleep well, and good night. There is one more soft fact to hold before we settle. The Milky Way, on a clear night away from any city, can be seen with the naked eye as a faint band of light stretching across the heavens. That faint band is the inner disk of our own galaxy, seen from inside. Every soft glow you can see along that band is a region of thousands of stars too distant to resolve individually. The dust lanes that cut through the band are the silhouettes of cold molecular clouds, dozens or hundreds of light years long, where new stars are quietly forming. The whole band, all of it visible at once, is just the slice of our galaxy we happen to be looking through from our position on the inner edge of the Orion Arm. The rest of the Milky Way, the parts you cannot see directly on any given night, is wrapped around us, above us, below us, all the way down to the floor of wherever you are listening from now. You have always been inside it. You will always be inside it. It is the standing place. And so, when the comparisons are done, the Milky Way is one galaxy among trillions, one bead on one thread in one corner of a cosmic web that fills a sphere 93 billion light-years across, with a wider universe beyond that, maybe hundreds of times larger, or may simply continue forever. The Milky Way is small by any largest-scale measurement. And yet it is also the only galaxy any of us will ever live inside. It is the one room you cannot step outside of, the one home you cannot photograph from the outside, the one slow turning that has always been with you. Whatever else the universe is, the Milky Way is yours. Let that be enough for tonight. Let the larger rooms fade gently into background. Let the Milky Way hold you for now.